Hey guys, today we are going to start talking about basically what half of calculus is, and that is the derivative, right? So differentiation and figuring out what the derivative is. It comes from limits, so you have to know what a limit is in order to develop this definition, but it's way more prevalent in calculus than limits themselves are. So when you are talking about derivatives at the very end of calc, that's going to be the word that probably sticks out to you the most, okay? And so when we talk about derivatives, the first thing we're going to look at is the slope of a line. So you learn about slope starting as early as like 8th grade math maybe, or at least algebra 1. And so we know a couple of different phrases about what slope of a line is, right? So slope of a line is rise over run, right? It's your change in y over your change in x, delta y, delta x, right? And more specifically, we want to get really good at identifying, instead of using y's, right? In higher level math, we use f of x, right? So it'd be like if you had the point a comma f of a, right? That'd be some value and then the function of that value, and then b comma f of b, right? If I wanted to find the slope between those 2 points, you would do f of b minus f of a over b minus a, right? Because this is y2 minus y1 over x2 minus x1. That's another one we can stick on here, right? These all represent exactly the same thing, and that is slope. Slope of a graph, so if I had some sort of function, so if I had a function, and you should be writing and drawing all the things that I'm writing and drawing, right? So if I had some function and I was trying to find the slope between 2 points, right, we would be finding the slope of technically what's called, wow, maybe if I drew a straight line through those, this is what's called a secant line, right? Because it is the slope between 2 points. This is what's known as your average rate of change. And this is very important for us. So for example, if I was looking at the average rate of change or the average speed of somebody riding a bicycle. So they start off a little slower and then they start riding faster and faster and faster and faster and faster over time. But we can figure out their average speed from 1.5 seconds, which is this point right here, to 5 seconds, which is this point up here. And basically what we're doing is we're finding the slope, that's pretty close, that's as close as I'm going to get, of that secant line, right? So I'm doing rise over run. And to do that, we kind of can use our f of b minus f of a, or y2 minus y1. So I'm finding f of 5 minus f of 1.5, oops, all over 5 minus 1.5. So like if I go to 5, looks like I'm at 40. And then if I go to 1.5, that's at 5. And then 5 minus 1.5 is 3.5. So really I'm doing 35 over 3.5, which is 10. And then I want to make sure I'm using my units correctly, right? So my distance was being measured, my y values, or excuse me, my function was being measured in meters this whole time. So this is actually 35 meters over 3.5 seconds was what my x values were being measured in. So my speed is 10 meters per second. Okay, so I found the average speed of that cyclist from 1.5 seconds to 5 seconds. What calculus helps us deal with now is, what would I do if I wanted to know exactly how fast the cyclist was going at 3 seconds? So if I wanted to know precisely at 3 seconds how fast the cyclist was going, I could estimate from my graph, right? You can kind of try to figure out, but it would always be some sort of estimate, right? So like, or an average speed. So I would have from like 1.5 to 5 seconds, be like, well, they're probably going about 10. If you chose points that were closer, so if I chose like 1.5 and 4.4, right? That is a line that looks like it's getting closer and closer to the 3 seconds that I care about. And I could even choose points that are like really close to the 3 seconds. So if I chose 2.8 and 3.2, right? That's a line that gets even closer to exactly how fast I would be going at 3. So if you get the closer slopes, right? This was an average speed, this was a better average speed, this was an even better average speed. Ideally, what we would like to get to is that exactly at 3 seconds, I would like to pretty much get as close to 1 point as possible, because these all require 2 points. And I would like to find the slope at this exact value, at this exact point. And this line, the line that touches the graph just at one place and it has the slope at that point, is what's known as your tangent line. And so your tangent line, the slope of your tangent line, is what's known as your instantaneous rate of change. This is also what's known as our derivative. Okay, so we found an average speed. It was a pretty good estimate for the biker speed. We could find an even better average speed that would get closer and closer to this precise slope at 3 seconds, but you can't ever use an actual average to estimate it. You would need to know exactly at 3 seconds what your instantaneous rate was, right? Exactly how fast the cyclist was going at 3 seconds. So your averages that get closer and closer are better estimates, but it's not until we get to the exact point that your tangent line slope would provide us with the exact speed of how fast your cyclist was going. Okay, and that's the main introduction to what a derivative is in context. So go ahead and now, using that information, go try to do some of those IFs and answer questions about those things.